Good uh, day, everyone. Welcome back. Let's get started. So today we are working on Unit 1, Lesson 3, 1.3 from the textbook. And specifically, I will be showing the example for question number 12. Um, Question number 12 states, copy and complete the following table. In your table, highlight the graphical characteristics that are unique to each function and could be used to distinguish it easily from other parent functions. So here we have all the parent functions that you should have learned in grade 11. And we are just gonna, do a few, things to them, such as sketching them. So let's sketch f of x equals x. And I've already done that using a software here. It's called Desmos. You can Google it. And it's a nice graphing software. And you can just write the equation and it will graph it for you. So this is y equals x. Pretty straightforward, straight line. We know what the sketch looks like. What about the domain? What is the domain for a straight line like that? And we know that the domain is XER. Because x can be any real number. This function goes all the way to the left, it goes all the way to the right. So x is any possible value. Range, also same thing. This function goes all the way up, all the way down. So y is also going to be every single real number in this case. Sketch, we did it. It's on the other page. Intervals of increase. Now, what is intervals of increase? Intervals of increase is when the function has a positive slope, or when it's rising. So when it's moving to the right and up. And if you see, this function here is positive. It has a positive slope throughout the whole, time it exists. So therefore, the intervals of increase will be from negative infinity, comma, to positive infinity. And we're going to have nice round brackets there. In case you didn't know, when you're writing it in this notation, there's a difference between round brackets and square brackets. Round brackets are exclusive of the end points. So in this case, the end points are infinity, and you can never include infinity as a point because it's not a number. Whereas if, say, it wasn't infinity, say if there was another value, let's say like 0, and 0 was included, then you would have a square bracket because 0 is included in that interval. But in this case, it is infinity, so round brackets. What about intervals of decrease? Well, this function doesn't have any intervals of decrease, so you just write none. What about location of discontinuities and asymptotes? Well, if you look at this graph, is there a break, a hole, or can I graph this line without ever lifting up my pencil? And there clearly I can graph this without lifting up my pencil, so there are no discontinuities or asymptotes. Zeros are, remember, another word for roots, solutions, or x-intercepts. So what are the x-intercepts? If you take a look at it, fairly simple. X-intercept is at the origin. So my x-intercept is 0, 0. Y-intercept is also 0, 0 because that is when it also intercepts the y-axis. As for, let's see, symmetry. Is this an even or odd function? Two ways to determine that. One is graphically by reflecting it in the y-axis and then the x-axis and seeing if the function then looks exactly the same. Or algebraically, you can do it by substituting negative x into the equation. And since we know the equation is just f of x equals x, so we just sub in negative x here. And now, if this is equal to the original function, which it isn't, it would have been an even function. But if this is equal to the original function multiplying by a negative 1, then this is considered an odd function. So in this case, this is an example of an odd function. Because if I took just x and I multiplied it by a negative 1, I would get negative x. And that is exactly what I got here. So the symmetry here is odd. End behaviors. So end behaviors are essentially when you have a graph and you have the arrows to signify that it's stretching forever. So every time you see one of those arrows, you have to write an end behavior. Usually they go in the form of x. Let me just. Oh, I can't lift that. Let me send this down then. There you go. So usually it's in the form of x going to infinity. So when x goes to infinity, positive infinity, what's happening with y? So when x is getting bigger and bigger and bigger, what's happening to my y value? My y value in this case is also getting bigger and bigger and bigger. So my y value is also approaching positive infinity. And since we have another arrow, when x goes to negative infinity, meaning to the left, when x is getting smaller and smaller and smaller and smaller, what's happening to my y value? My y value is also getting smaller and smaller and smaller. So in this case, x goes to negative infinity, y also goes to negative infinity. So these are my end behaviors. This is how you would write that out. It's pretty straightforward. Let's continue for our next function, which is g of x is equal to x squared. So the sketch looks like this, and it's pretty straightforward. It's a parabola. So we have this sketch now. We can use this to help us solve some of these other questions. The domain. What is the domain for this function? Well, does this function go all the way to the left? Yes, it does. Does this function go all the way to the right? Yes, it does. So therefore, domain is pretty straightforward. X belongs to all the real numbers. What about range? Does this function go all the way up? Yes, it does. Does this function go all the way down? No, it does not. It doesn't go below a certain point. And what is that point that it doesn't go below? And you can clearly see it's the x-axis, or 0. So the range for a function like this is, I shouldn't write y anymore. I should write g of x, because we're writing in function notation. So g of x belongs to the real numbers, such that g of x has to be bigger than or equal to 0. Okay. And I know I'm just kind of squeezing it in here, but hopefully you guys can see. I might just use y, just because it's less writing for the next example. But just so you are aware, in grade 12 advanced functions, you are expected to use function notation. So maybe I should just keep it function notation, just to be consistent. Anyways, intervals of increase. So let's take a look at this graph here. When is this function increasing? Meaning, when does this function have a positive slope? If you take a look at this, clearly it's rising, so there is a positive slope. But if you start from the left here, it's going down. So that's not really a positive slope. So at what point does the positive slope start? And it starts at the vertex, so in this case 0, 0. So from 0 to positive infinity, we have a positive slope. So that's my intervals of increase. And intervals of decrease will then be from negative infinity, because all they're from the left, to 0. And at 0, the change occurs. So yeah. Is there any, discontinuities? There are none. This is a graph I can graph without lifting up my pencil. Zeros, in this case, zeros are 0, 0 as well, because that is my x-intercept. You can see x-intercept. That is also my y-intercept, so that's pretty straightforward. Now what about symmetry? So if you've forgotten, for symmetry, all you have to do is substitute a negative x into the function. So g of negative x is equal to negative x squared. And if I simplify that, it's still x squared, because negative x times negative x is x squared. And now this looks exactly like the original function. Therefore, it has even symmetry. And the other way to realize that is to take a look at it and see if there's a mirror image along the y-axis. So if there was a mirror on the y-axis, are these two mirror images? And yes, they are. So pretty straightforward, even symmetry. End behaviors. End behaviors, once again, there would be two arrows moving on, one to the left, one to the right, showcasing that this function is continuing on forever. because it does continue on forever, we can write our end behaviors. So x, when x goes to positive infinity, what's happening with y? So when x is getting bigger and bigger and bigger, what's happening with y? Well, y is getting bigger and bigger and bigger. So y, when x goes to positive infinity, y also goes to positive infinity. But what about when x is getting smaller and smaller and smaller? So when x is going to negative infinity, what's happening with y? Y is getting bigger and bigger and bigger. You see it's going up. So y is then going to positive infinity. And this is the end behaviors for a quadratic function. So end behaviors are always written in pairs, remember? So x does something, and then you have to tell me what's happening with y when x is doing that. Okay, so let's continue. We're going to actually stop here. I'm going to do the others in a different video.